Good morning, jurors. We are NYGH Team 1 consisting of
Jessie,
Hoiling.
and Wensin.
We will be presenting on our main problem, hand helicopter. In our analysis of the question, we noted that the liftoff and maximum heights of the hand helicopter as the dependent variables. The hand helicopter flies up due to Newton's third law of motion. As the blades rotate, the blades push the air down and the air exerts a force of equal magnitude and opposite in direction on the blade, resulting in lift. Lift and drag act in opposite directions. In our experiments, we made some of the variables and equations and factors that affect lift and drag the independent variables. We conducted our experiments by manually launching the hand helicopter and filming the videos using slow motion. In our setup, we used the measure application to minimize parallax errors due to a tilted camera and used the slow motion function to record at a greater frames per second, among other measures. To analyze the data we collected, we used Tracker to track the motion of the hand helicopter, specifically its initial vertical component of velocity and the maximum height. These are the independent and dependent variables we analyzed.
In the first experiment, we investigated how the mass of the hand helicopter affects its maximum height and put the blades into different mass categories. The graph of maximum height against initial velocity for different mass shows that 1.8 gram is the optimum mass for the greatest height. However, by theory, the lightest blade should fly the highest. One possible explanation is that the blades with 1.7 grams are less stable than that of 1.8 gram. Thus, more wobbling is induced. More energy is converted into gravitational potential energy, and the hand helicopter reaches a greater height. However, the blades of 1.9 gram are too heavy. The net force upwards is smaller than that of 1.8 gram blades due to more weight, and thus it reaches the least height. In our second experiment, we investigated how the chord length affects the maximum height and the liftoff. This graph shows maximum height against initial velocity for various chord lengths. The 8 cm blade has the greatest maximum height. We can conclude that the longer the chord length, the higher the maximum height. For this graph, it shows chord length against initial velocity. We analyzed that the range of initial velocity increases as chord length increases. This shows that the greater chord length is able to result in a greater initial velocity. Increasing the chord length increases its aspect ratio. A long and narrow wing with a high aspect ratio has a greater lift-to-drag ratio compared to those blades of lower aspect ratios. In simpler terms, a blade with longer chord length is able to push down a greater volume of air compared to those blades with shorter lengths. In our third experiment, we investigated how the blade angle affects maximum height. Blade angles is defined as the angle from the horizontal. To vary the blade angle, we heated the blades and altered the blade angles, using a vernier caliper to check for accuracy. This is the graph of height against blade angle for various initial velocities. As the blade angle increases from 15 degrees to 30 degrees, the maximum height decreases. As the blade angle increases from 30 degrees to 45 degrees, the height increases. Thus, we will be looking at this graph in the two sections. When the blades rotate, they push down the air. The air then pushes back onto the blades at 90 degrees, according to Newton's third law of motion. This reaction force has vertical and horizontal magnitude since the blade has an angle from the horizontal. The vertical force is responsible for lifting the hand helicopter up. As illustrated with the annotations, when values are substituted in, given that the air exerts the same force on the blades, theta of the smaller blade angle is larger than alpha of the greater blade angle. Hence, the smallest blade angle, 15 degrees, has the greatest vertical component force and reaches the greatest height. By theory, this section of graph should observe the same trend. The greater the angle, the lower the maximum height. However, the graph shows that the maximum height decreases. This is observed due to a limitation in our experiment. Due to manual bending of blade angle of attack is formed when blade angle is high. Higher angle of attack causes a greater lift coefficient. I will explain this in detail. This involves the Cohen-Dye effect. It is defined as the tendency of a moving stream of fluid to follow an adjacent flat or curved surface and to entrap fluid from the surroundings, rather than continuing traveling in a straight line. Air will follow the surface of the blade due to Coanda effect. With greater angle of attack, air is directed downwards to a greater extent, and using the same concept as explained earlier, it results in greater lift. In our fourth experiment, we investigated how the height at launch affects the maximum height of hand helicopter. This is the graph of height against initial velocity of different launching heights of hand helicopter from the ground. This is the graph of height against initial velocity for different launching heights of the hand helicopter from the ground. When the hand helicopter is 25 centimeters from the ground, it is able to fly higher than when it is 75 centimeters away from the ground, comparing the same initial velocity. The closer the blade is from the ground, the greater its maximum height. When the blades are further away from the ground, the downwash is able to dissipate into surrounding air. When the blades are closer to the ground interferes and reduces the induced airflow. More air is pushed back onto the blade and lift increases.
In our fifth experiment, we investigated how the number of blades affects the maximum height. We cut our blades and hot glued different number of blades together while ensuring that the center of gravity is balanced by making the angle between each blade the same. Then, we checked for mass differences between the different hand helicopters and added blue tag accordingly to ensure that they are of the same mass. The graph of maximum height against initial velocity for different number of blades shows that the hand helicopter with 3 blades flew to the greatest height, followed by the hand helicopter with 2 and then 4 blades. When the number of blades increases, the surface area of the blades increases, so the drag increases. Therefore, supposedly, the optimum number of blades should be as small as possible to decrease drag. However, a hand helicopter with 1 blade is unbalanced due to its misplaced center of mass, so it does not fly. A hand helicopter with 2 blades may sometimes cause gyroscopic precession, resulting in wobbling which reduces the lift. A hand helicopter with 3 blades has the optimal balance between stability and drag. A helicopter with 4 or more blades experiences a much greater drag even though it is stable, which lowers its maximum height significantly. For these reasons, hand helicopters designed with 3 blades are the ideal compromise between the amount of drag experienced and its stability. Therefore, 3 blades is the optimum number of blades to generate lift and for the hand helicopter to reach a greater height. Next, we will be covering the conclusion. By theory, the smaller the mass, the higher it will fly. However, the experimental findings did not support the theory. This may be because the difference in mass was not significant enough to show a significant difference in the flight of the hand helicopter. It could also be due to the fact that our data is not large enough to observe significant difference. By theory, the longer the chord length, the higher the aspect ratio, thus the greater the maximum height of the hand helicopter, and indeed, our findings align with the theory. By theory, a smaller blade angle will yield a greater height, and our experimental conclusion showed that. For number of blades, the theoretical outcome was that 2 or 3 blades should fly to the greatest height, and our experiments showed that 3 is the optimum number of blades. For the ground effects, the theoretical outcome was that the lower the height of the launch from the ground, the greater the maximum height of the hand helicopter due to ground effects. This is proven in our data. These are the possible sources of error for our experiments. As we tracked the position of the hand helicopter manually, the position of the hand helicopter that was tracked may not have been the actual position of the hand helicopter. We used our hands as a launcher, so there may be human error as we may have launched the hand helicopter at a slight angle. The texture of our hands is also not consistently smooth, which will reduce precision. The rigidity of the blades also could not be quantified or kept constant. There is a parallax error when tracking the hand helicopter when it flies too close to the screen, as it will appear to be bigger and fly higher due to foreshortening. The center of weight may not have been maintained, and also due to the manual alteration of the blades and the blue tag that was added to the blades. Below were some of the limitations that we had. Firstly, we made modifications to the blade by cutting and gluing the blades together. This meant that we could not be precise in the variables, as there is bound to be human error in altering the blades. However, due to factors such as the initial width being too narrow to be varied substantially, and the blade rigidity becoming extremely compromised when we cut off a long strip of plastic, the results were inconsistent and could not be used. Thirdly, there was an induced angle of attack when we altered the blade angles, which caused the data to be skewed. This is our error analysis. This is the end of our main problem, hand helicopter.